We were discussing continuous random variables yesterday. We said a random variable x is continuous if the probability law p x is an absolutely continuous measure with respect to the Lebesgue measure, right. So, we said so p x is absolutely continuous with respect to lambda, which is the Lebesgue measure. In other words, this means that every Borel set of Lebesgue measure 0 has p x equal to 0. Okay. And then we said there is this Radon-Nikodym theorem, which we only stated, which we will not prove. We said that for every Borel set, so there exists so if p x is absolutely continuous with respect to lambda, there exists a measurable function f x from r to 0 infinity. So, this is a non negative measurable function such that for all Borel sets p x of b is given by the integral over b f x d lambda. So, this is a Lebesgue integral. You can just look at, you can just view this as the probability of the set p x of b being given as the integral over set of this function, right. This function we said is the probability density function of this random variable. So, Radon-Nikodym theorem is the result that asserts the existence of a density for a continuous random variable. Okay. And so, this, so some people write this in notation as, so this is notation. So, they write d p x over d lambda equal to f x. So, this looks as though this is the derivative of this measure with respect to that, right. So, this is known as the Radon-Nikodym derivative. Okay. So, this is just notation, and the Radon-Nikodym derivative of the probability measure p x with respect to the Lebesgue measure lambda is your probability density function PDF. Okay. So, the interpretation of this is that, see, if you have a set of very small Lebesgue measure tending to 0, its probability measure will also be very small, right. So, if you take a very small Lebesgue measure set, its p x will also be very small. So, you divide that measure over the small Lebesgue measure, you will get a function, right. So, what you get will depend on where you are on the real line, and that is your probability density function. Okay, that is the interpretation of this Radon-Nikodym derivative. Okay. Are there any questions? So, that is really all there is to a continuous random variable. So, and then we started looking at some examples, right. The first example we looked at is our familiar uniform measure, uniform random variable, which puts a uniform measure in some interval a b or 0 1 or whatever. Then we looked at the exponential random variable. The exponential random variable has a remarkable property that it is memoryless. So, if you know that the light the life of a light bulb is, for example, exponentially distributed, you know that if the bulb has been glowing for a certain amount of time, the further time that it will glow will also be distributed as the unconditional lifetime, right. So, because it is memoryless, we proved it. In fact, we also said that the exponential distribution is the only memoryless distribution among continuous random variables, right. So, we will look at a few more examples, maybe couple more examples. So, example 3, that of a Gaussian random variable. So, this Gaussian random variable is probably the most important of all these continuous random variables. if there is so this is if you have to pick one distribution as the single most important distribution among continuous random variables, it has to be the Gaussian distribution, Gaussian random variable. It is a 2 parameter distribution, okay, and I will specify. So, the probability density function is easier to specify for the Gaussian. So, mu is some parameter in R and sigma is some parameter in R plus, okay, it is strictly bigger than 0. For it is parameterized by 2 things. Remember the exponential was parameterized by 1 lambda, right. So, this is parameterized by 2 things and its density is given by f x of x is equal to 1 by sigma square root of 2 pi e power minus x minus mu squared over 2 sigma squared. Okay. So, this is for all x in R. So, if you just look at the density, so if you have your mu which could be positive or negative, I am just drawing it as negative. So, this distribution will be symmetric around mu, as you can verify, right, and then it falls off very quickly like e power minus x squared, right. So, it starts off at the value, what does it start off at, x is equal to, so it starts off at 1 by sigma square root of 2 pi, right, yes, and then it falls off very quickly, looks like that, okay. And so, this is your mu, and if your sigma is small, then this height will be quite high, this will be quite high, but its rate of fall will be even quicker, right, it will be very peaked, whereas if your sigma is large, it will be more spread out, right, this curve will be more spread out. And if you have, so for a standard, what is known as a standard Gaussian or a standard normal, so this is also known as normal random variable. Standard Gaussian, you have mu equal to 0 and sigma equal to 1, then you have f x of x is equal to 1 by square root of 2 pi e power minus x squared over 2. Right, this is called standard Gaussian. This will be centered at 0. So, this Gaussian random variable occurs very commonly in practice. In particular, for example, if you measure the noise across a resistor and try to plot a histogram of how it is distributed, it will be distributed like a Gaussian, right, and there are several, I mean there are innumerable number of places where this Gaussian distribution occurs. The importance of the Gaussian PDF is because of 2 reasons. One is that it is what is known as a stable distribution, which we will study later. So, if you keep summing independent Gaussian random variables, you will get a Gaussian random variable, which this is something we will study later. So, it is stable under summation, right. Also, there is a very important theorem known as central limit theorem, which says that even distributions which are not Gaussian, if you keep adding those random variables, independent random variables which are even not distributed as Gaussian, you will eventually get to a Gaussian, right, and that is a theorem we will do towards the end of this course, right. So, the Gaussian random variable has some very remarkable properties. So, it is stable and it is an attractor, and therefore, it is great importance. Okay. So, if this is just the PDF, the CDF is so if you want to take the CDF of the standard Gaussian, it will look like So, it is just for the standard Gaussian it will look like this, right, 1 over square root of 2 pi e power minus y square over 2 dy, is not it. So, this integral cannot be expressed in closed form, okay. It is just whatever it is, it is just an integral, and this is known as the error function f of x. So, error function is simply the CDF corresponding to the it is the CDF corresponding to the standard Gaussian, okay. And this error function, yeah, as I said, it is not available in closed form. There are some approximations available, and in the old days these were the error functions were tabulated just like logarithms were tabulated, right. But in this era of computers we do not need to, I mean we just give it to MATLAB and you can get the error function values at whatever x you want. Are there any questions? So, this mu and sigma have, so the mu has the interpretation of the mean and sigma has the interpretation of standard deviation. We will get to that much later, okay. Are there any questions at this point? Yes, that is also an equivalent definition. So, we did not define it that way, but you can, I think this book by Grimmett and Sturzaker says that x is a continuous random variable if capital f x of x can be written as the integral of some function, some non-negative function.
So, if I take any function and write its integral, that can be
sorry?
If I take some function f x, small f x, and integrate it.
Yes. So, what you can do, so if you take any small f x which integrates to 1, non-negative function which integrates to 1, then that should correspond to some random variable, right, because your properties of CDF will be satisfied.
Is that how Gaussian works?
No, see the people figured out that certain distributions occur very commonly in real world, right. So, it was not, I mean this was, so the theory of probability came much later, right. So, people figured out that this kind of bell curve, this bell curve is occurs everywhere from, you know, heights of students in class to resistor noises, right. So, they all follow this kind of distribution and people knew this for a very long time. So, I am just saying the CDF does not have a closed form, the PDF has a nice form, right. And obviously, this PDF does not have any interpretation of probability as I said yesterday, because this could be very tall, right, this could be very peaky and it does not have any interpretation of probability. Only when you integrate the PDF can you speak of probabilities, right. So, right, so that is the Gaussian. We will keep coming back to this, okay. This is a very important distribution. I will just give one more example. This is that of Cauchy distribution, Cauchy random variable. I will just give the, I will not parameterize it, okay. I will just give the unit version of the unit Cauchy, so to speak. So, the density is given by f x of x is equal to 1 over pi 1 over 1 plus x squared x in r, okay. So, if you want to parameterize it, you have to put x minus x naught whole square and some gamma here, so it is just distracting, let me not do that, okay. So, this guy, so as you can see, I mean this is a valid distribution, of course, I mean first of all you have to verify this is a valid distribution, right. You have to integrate minus infinity to infinity and say that this is equal to 1. It's even that is not very easy to do. I forgot to mention that the integral, if you just integrate this guy from minus infinity to infinity, it is equal to 1, but showing it is not the easiest of integrals to do, right. You have to go into the complex plane, integrate over a contour and do some complicated stuff to get this answer equal to 1, okay. But it is true. Here it is much easier if you want to verify this is a valid probability density function. You want to say that the integral minus infinity to infinity, this is equal to 1, this will be a inverse tangent, right. So, you will get your, this is easy to do. So, this also, so this looks like also it is symmetric around 0. So, yeah, so the CDF of this will be a inverse tangent, right. You can write integral minus infinity to y or whatever and get an inverse tangent formula for the cumulative distribution function. Again, if you plot this, it also looks, so it starts off at 1 over pi, does not it, and then it falls off rather slowly, right. It falls off only as 1 over x squared, isn't it. For x large, it falls off as 1 over x squared. So, the exponential distribution falls off as, it falls off exponentially, right. It falls off as e power minus lambda x. This is an exponential fall which is very quick. This is even faster, this is e power minus x squared, right. So, the Gaussian decays very fast, whereas this decays only like a power law, right. It looks like x power minus 2, okay, with me. Yeah, so there is a qualitative difference between this Cauchy random variable and random variables such as Gaussian or exponential and the uniform, for example. The uniform is bounded, right. It only takes values in a bounded set, right, a to b, for example. So, it is deterministically bounded in that interval. The exponential, Gaussian, Cauchy, they are all actually unbounded, there is no deterministic bound on the values they can take, right. If you look at the exponential and the Gaussian, the probability of taking very large values falls off very rapidly, right, falls off exponentially or even faster than exponentially in the case of the Gaussian, whereas in this case the probability of taking large values is not negligible, it only falls off as some x power minus alpha, here alpha is 2, right. So, these kind of random variables which the probability of taking large value falls off slowly. So, this is called a heavy tailed random variable, because I mean the it is like a power law, right, it falls off like a power law, whereas the exponential and the Gaussian random variables, they are all examples of light tailed random variables. So, they are very qualitatively different. So, if you have a heavy tail random variable like a Cauchy random variable, it will take fairly large values with non negligible probability, okay. Are there any questions? So, there are many other distributions which are continuous random variables, but most of them are derived from some these important distributions or generalizations of these distributions. Okay, there is all this gamma, chi squared, log normal, this and that, they are all various variations of exponentials or Gaussians or they are obtained from transforming these random variables in some way, right, which we will get to them later. So, at this point all you really need to know is really uniform, exponential and Gaussian, and this is bit of an odd one out because it is heavy tailed, right. This has some fairly bizarre properties, we will see later. Are there any questions? So, this is called a two sided Cauchy, okay, because it is symmetric around 0. There is a one sided Cauchy if you put 2 over pi 1 over 1 plus x square and define it over x greater than or equal to 0, then this part will go away and then you will have something that is twice as tall only falling off like that, right, that is called one sided Cauchy, okay. You can have parameters, you can have. So, normally you have, you can write x minus x naught whole squared, and let me see. So, you have, so normally you have gamma squared, gamma, this is the parameterized version. I just wrote the standard version of the Cauchy. Okay, you can again verify that this is a valid PDF by just putting x minus x naught over gamma as some y or something and integrating. Okay. This is the parameterized version of Cauchy, now that you asked. So, just like so for discrete random variables, it is enough to specify the probability mass function, and for continuous random variables it is enough to specify the probability density function or the Radon-Nikodym derivative, which is the same thing, because you can integrate it out to find the probability law, right.